Okay, this is the review for Unit 7 for BC Calculus. It's the parametric and polar unit. Make sure you're kind of able to hit all of these bullet points in addition to the review. I think most of them are covered on there. So, for the set of parametric equations given by x and y, we want to find the derivative. So, remember the derivative dy dx is going to be dy dt divided by dx dt. So you can even write dy dt over dx dt. And then you're going to just take the derivatives. So the derivative of y here, that's just going to be 2t minus 3 over the derivative over here is going to be negative 3t squared. And you can't do anything with that, so there's your final answer for that part. Now it says, find the equation of the tangent line to the curve when t equals 1. Remember, the equation of the tangent line, that means take a derivative, plug something in, and then use the point-slope formula. Well, we already took the derivative up in part A, so now we need to plug something into that derivative. Well, I'm going to plug in this t equals 1, so basically you could just say something like dy dx evaluated at t equals 1, means all I'm going to do is drop a 1 in wherever there's a t, and 1 squared is still 1. And then you could just kind of clean that up. Let's see, that's going to be a negative 1 over a negative 3, so it'll be a positive 1/3. And then from there, you need to use point-slope formula. The problem is that this is our m, right? So we have m right there. We still need to figure out our y1 and our x1. So to figure those out, you could say something like at t equals 1, right? So x equals, all I'm going to do is plug in t equals 1 into the x equation. So 1 minus 1 is 0, right? Because it's 1 minus 1 cubed equals 0. And then I need to figure out what y is as well. So still at t equals 1, I take it and I plug it in there. So that's 1 minus 3 plus 2. So 1 minus 3 plus 2. Nope, sorry. 1 minus 3 plus 1. There we go. That makes more sense. So that's negative 2, negative 1 there. So this gives us our x1 and our y1, and now we have our m, so we can just drop those into y minus y1, so minus a negative turns to a plus, equals my m is 1/3, parentheses x minus x1, which is 0. You could say stop it there, or you can go ahead and clean it up. If you wanted to rewrite it, if it was, for instance, multiple choice, you could rewrite it like that for part B. Okay, moving on to part C. Find all points of horizontal and vertical tangency. So for horizontal and vertical tangency, you need to pay attention to the slopes, and when the slope, aka the derivative, is either 0 or when it is undefined. Okay, so I'll do horizontal tangency first. So horizontal tangency, that's going to occur when the derivative equals 0, aka the numerator equals 0. Alright, well, again, what numerator am I talking about? I'm talking about from part A, right? This is the slope. This is the derivative. So you have horizontal tangency when the slope equals 0. Well, this thing is going to equal 0 when the numerator equals 0. So basically, I'm just setting the numerator equal to 0, and then that's going to give us 3/2 there. So we have that, and then find all points. So make sure you're answering the question. This tells me at t equals 3/2, I have horizontal tangency. But to get the point, I then need to take that 3/2 and plug it back in to the x and plug it into the y to get a point. Remember, a point is an x comma y. So I'll just plug that in. Sorry, I'm running out of a little bit of room here. So let's see, that's going to be 1 minus 3/2 squared, so what is that? That's going to be, I'll turn it into eighths, 8/8 minus 27/8. Ooh, this one is not nice. So I have negative 19/8 as my x coordinate. And now I need to pay attention to my vertical tangent. Oh, no, I need my y value. Alright, so to get the y value, so I'll say y equals, and again, I'm taking this t value and plugging it into y. So that's going to be that squared minus 3 times 3/2 plus 1. And after some math there, that is going to equal -5/4. So my horizontal tangency occurs at the point -19/8, comma, -5/4. So we've got that. Okay. Now, I didn't answer the full question because now I have to do something similar but with vertical tangency. So vertical tangency occurs when the slope is undefined. Well, that happens when the denominator is undefined, or when the denominator does not exist, aka your denominator equals to 0, okay? So, yeah, vertical tangency occurs when the slope is undefined. The slope here is going to be undefined when the denominator equals 0. So you could say the denominator is 0, aka slope undefined, same thing. Okay. So we want the denominator equal to 0, so that's -3t squared equals 0. That occurs at time 0, okay? And so at time 0, I need to get an x value and a y value. So now I have to say at time 0, x equals 1 minus 0, which is 1, and y equals, if I plug in a 0 there, that's 0 minus 0 plus 1 equals 1. So my vertical tangency occurs at the point 1, 1. That is a much nicer point than the horizontal tangency. Okay, moving right along. So we're going to have number 2 here. Scooch this up. Okay, so number 2, for the set of parametric equations given by x and y, find the slope again, and find the equation to the tangent line when t equals, oh, I think I changed that on yours to be t equals 4. Okay, so here I'm just going to rewrite this as t to the 1/2, okay, and so then I'm going to find the derivative. So this derivative is the same thing. It's going to be dy dt divided by dx dt. And so with parametric, now I can take the derivative of y, right? So the derivative here is going to be 1/2 t, okay, 1/2 t to the -1/2. Well, think about what that means. So it's 1/2 t to the -1/2, okay, over, and then you can take the derivative of x, so that's going to be 2t plus 1. So I'm just going to kind of clean that up a little bit. I'm going to say that this t to the -1/2 means it's going to go into the denominator, and it's going to be a square root. So I'm going to rewrite it as 1 over 2 square root of t over 2t plus 1 there. Alright, so there is my derivative. And now find the equation to the tangent line when t equals 4. I think I changed that on yours, so I'll change mine to be consistent. Okay, so what I'm going to do here is plug in t equals 4 into the slope. Okay, remember, equation of the tangent line. What do we do when we find the equation of a tangent line? You take a derivative, check, you plug something into that derivative. So basically what you're doing is you're evaluating the derivative at a certain time. Oh, I see why I changed it to 4. It makes it much easier to take the square root. Okay, so when I plug in a 4 there, okay, square root of 4, and then over 2 times 4 plus 1. Okay, so we're going to clean that up. So let's see, that's 2 times 2 is 4, so it's 1/4 divided by 9. And so you could do a keep change flip there. Basically, that ends up to be 1/36. Okay, so again, this is the m in my point slope formula. So for the point slope formula, I need to get a point. Notice I don't have a point anywhere, so I need to do a little bit of work to get the point. So you could say something like at t equals 4, and now I'm going to evaluate x and y. I'm going to use the equations given in the beginning. So x equals, well, at t equals 4, that's going to be 4 squared is 16 plus 4. So I get a 20 for the x coordinate, and now I want to get the y coordinate. So I take t equals 4 and I plug it in there. Square root of 4 is going to be 2 there. So when I evaluate that, just write it's 2. Okay. So now I can go ahead and plug into the point slope formula. So it's y minus y1, so minus 2, equals my m is 136, parentheses x minus x1, which we said was 20. I would highly recommend safe stopping that. Okay, I would safe stop this right here. If you insist and you really want to distribute the 136, distribute this over there and then move the 2 over, I believe the final answer you would get would be something like 136x plus 13 over 9. Okay. So there is page 1 of the Unit 7 review. Okay, this is number 3 on page 2. So again, it says find the derivative for the parametric curve defined by, and they give us an x and a y. We've been kind of preaching that dy dx is dy dt divided by dx dt. So if you want to define them separate and then put them all together, you can. So I'll just say dy dt equals, alright, so here's why. So now we're taking the derivative of ln of the junk. So the derivative of ln of the junk is 1 over the junk times the derivative of the junk. So it's 1 over that t squared plus t times the derivative of that. So it's 2t plus 1. So if you wanted to clean that up, you could write it as 2t plus 1 over t squared plus t. So that's the dy dt. And then you're going to do dx dt. Okay, so dx dt, I'm looking over here. It might be helpful for you to think of this as to a 1/2 power. Okay, so I might kind of rewrite that up here. Hopefully you can see that. Equals, that's the same thing as this to the 1/2 power. Okay, so now when I take the derivative of that, it's going to be a chain rule, right? So this 1/2 comes out front. So you are going to have 1/2 of that. So you recopy the inside. You decrease the exponent by 1. So 1/2 minus 1 is negative 1/2 times the derivative of the inside, which is 2. Okay, so cleaning this up a little bit, the 1/2 and the 2, those take each other out. And then this negative exponent means that it's going to be 1 over this thing. Okay, so you can say it's 1 over this thing to the 1/2, which we all know is the square root. So I'm just going to rewrite it like that. And now it's just going to be those two things matched up together. Okay, so you can rewrite it as this divided by that, or you could do a keep, change, flip. So you could say that dy dx is going to be this thing divided by that. And again, if you looked and that was maybe not a multiple choice, they may do a keep, change, flip kind of thing and write it like this with the t, and then obviously changing this to multiplication, and then you would flip this. So really that just becomes your new numerator. You can have this, and it might be written something like that. Okay, either of those would be acceptable. Your safe stop would be over here though. Okay. Alright, that's 1 through 3. Okay, let's move on to number 4. It says a parametric curve C is given by x and y here. Write the equation of the tangent line to C at a given point. So remember, equation of the tangent line, we know how to do this. We've been doing it since September. So to write the equation of the tangent line, my plan is to figure out the slope. Slope in calculus is derivative. So first I need to take a derivative, and then I need to plug into that derivative. That will give me the m value for the slope. Once I have that m value, then I can use the point slope formula as needed. So first we are going to figure out the derivative. Well, the derivative here is going to be dy dx, so we first need to figure out dx dt and dy dt. That way we can figure that out. Okay, so first we'll figure out dy dt. So in this case, dy dt, here's my y, that is going to be a product rule. So you're going to have first times derivative of the second. Well, the derivative of that is just e to the t. So you're going to have t, e to the t, plus second is e to the t, times the derivative of the first. Well, the derivative of t is just 1, so that's that. Next, I need to figure out what dx dt is. So the derivative of ln of t is just 1 over t times the derivative of t, which is just 1, so it's just that. So keep in mind, this tells me that my dy dx, the derivative, is going to be this part divided by that part. Well, this divided by that, same thing as multiplying by the reciprocal, right? So basically, I'm multiplying this whole thing by t. So in other words, it's t times that first part. And again, you could get that by doing a keep, change, flip. So we could also say this is t squared e to the t plus t e to the t. Okay? So that is my equation for the slope. Now, if I actually want to get the m, I need to take, and I have to take that and I have to plug into that. Okay? So essentially what you're doing is you're evaluating the derivative. The problem here is that we weren't given a t. So first, in order to be able to evaluate the derivative at a certain time, we need to figure out where is this thing, what is the time I need. To do that, you're almost going to have to work backwards here. They did give us a point, okay? So what we need to do is plug in the point to figure out what t is at that certain point. So if you kind of say, well, x equals ln of t, and if the x value is 0, you could say something like at x equals 0, right? So 0 equals the ln of t. So then you can undo each side by e and e both sides. So then you have e to the 0 is 1 equals t. So now we have a time, okay? So now you can take your slope, or your derivative here, and evaluate it at t equals 1, because now we actually have a time to plug in. So once you have that t, go ahead and plug that in. So we take this t, plug it into this equation here, kind of ran out of room. So it's going to be 1 squared is 1, e to the 1, right? And plus 1 times e to the 1, which if we just kind of clean that up, that's just e plus e again. So really that's 2 e's, because e plus e is 2 e's. So this is the m. This is your slope. And now we want to plug that into y minus y1 equals m, parentheses x minus x1. We're going to use our point slope formula. This is the m. Y minus y1, so that's y minus e, okay, equals m. That's 2e. Parentheses x minus 0, if you want to do that. And you could clean that up a little bit if you wanted to. You could safe stop it. I'll just clean this one up since it's not so bad. Plus an e over there. Okay, and that's how you do number 4. Okay, moving on to number 5. Let me scooch this up a little bit. Okay, so in number 5, this has an A, B, C, and a D. This is very similar to one on your test, so I definitely know how to do something like this. It says, find the slope, not the equation, of the line 2C when t equals 3. Okay, so the first thing you're going to need to do here is find your derivative, your dy dx. And we already know dy dx is dy dt divided by dx dt, just like before. Okay, I'm going to do that all in one step because I don't have that much room here. So dy dt, that's going to be 3t squared and minus 3. Over, now dx dt, that'll be 3t squared minus 6t from there. And now what we want to do is evaluate that at time of 3, where in the last problem we needed to get the time first. Here they gave me time is 3, so I'm evaluating that at t equals 3. So all I'm doing is taking this 3 and plugging it in. So 3 squared is 9 times 3. That gives me a 27 minus 3 over, and again, that's going to be 27 again. And that'll be minus 18. And so I think you can clean that up, right? That's 24 over 9. And if you wanted to reduce it a little bit, you can call that 8/3. So again, this is your slope, okay? That's the m value. Oh, and that's all it was asking for in 1, so I can stop there, okay? At what point or points is the tangent line to C vertical? Is the tangent line vertical? You have to think about what that means. The tangent line is vertical. Well, the tangent line, you're thinking derivative. You're thinking the slope. So they're saying, when is the slope vertical? Well, the slope would be vertical. The slope of a vertical line is undefined. So when would the slope be undefined? Well, looking at your slope, when would this thing be undefined? That occurs when your denominator is 0. When your denom equals 0. When the denominator of the slope, right, equals 0. So all I'm going to do is take this denominator and set it equal to 0. Okay, you'd probably do yourself a favor by factoring out a 3t there. Fill up a t minus 2. And that gives you times 0 and time 2. Okay? So let's see, and it says which points. Notice, these are not points. Those are times. Points have an x and a y value. So then you need to take a second and just say something like at t equals 0, right? You need to take this t equals 0 and plug it in to get your x and your y. Well, when t equals 0, that's 0, and that's 0, right? So you'd say x equals 0, y equals 0, aka your point is 0, 0. That one's easy. Okay? Now, at t equals 2, might have a little bit more math. Let's see. When t equals 2, you need to plug in, so you'd say something like 2 cubed minus 3 times 4, so that's 2 cubed minus 3 times 4. Well, that's going to give you a, what is that, 8 minus 12, negative 4. And then y equals, you can do the same thing, but you got to plug in. So that's going to be t cubed minus 2, 3, 6. So that's 8 minus 6 is 2. So your point there would be negative 4, comma 2. Okay. And it's never enough to be able to know when the tangent line is vertical. Now they're asking for where is it horizontal. So just like the vertical tangency occurred when the denominator was 0, horizontal tangency occurs when the numerator equals 0. Okay, so I'm going to go back up to my slope from up here and set the numerator equal to 0. So this thing equals 0. And you can factor out a 3 if you want to. It doesn't really matter though. I'm just going to say that 3t squared equals 3. So t squared equals 1. So the square root, remember, is plus or minus 1. Okay. So, and very similar to up here, you have to do each one. At t equals negative 1 and at t equals 1. And then you have to plug each of those in to the x and the y to get the actual points. So when you do this, x equals, when you plug in a negative 1, a negative cubed is negative. Negative squared is positive 1, but then it's minus 3. So you've got this. So that equals negative 4. And let's see the y value at negative 1. When you plug in a negative 1, that's going to be a negative 1 plus 3, so that gives you a 2. So again, the point there would be negative 4, 2. And at positive 1, when you plug in a positive 1, you get 1 minus 3. Okay, so that's a negative 2. And the y value, when you plug in a 1, you get 1 minus 3. Well, so that's a negative 2 as well. So you just get negative 2, negative 2. And they're not always the same like that, but just happen to be in this pattern. Okay? Alright, so part D says, find the length of the curve find the length of the curve from t equals 2 until t equals 5. So, your setup for here, remember the arc length, it's going to be an integral. They gave me the interval of the integral. Oh, that's fun to say. And it's the square root. And remember, it's dx squared plus dy squared, all with respect to t, of course. So my dx squared, right, and your dy squared, I've got those things. Let's see, here's my, oh, you can't see it. X up here, so dx, dy, so you actually have to take those and square it. So it's going to be 3t squared minus 6t. So it's that quantity squared plus, now the derivative of that. So that's going to be 3t squared minus 3 quantity squared. You can use your calculator via Math 9. Okay. And when I plug that in, I got 121.409 as my answer there. Okay. Alright, so that is page 2, and I'm going to switch up and we'll move to page 3 here. I'm going to scooch this down. Alright, an object has a position vector given by s of t. Find its velocity vector, the acceleration vector, and the speed at time equals 1. So, given position, I need to go to velocity. To go from position to velocity, you're just going to take a derivative. So the velocity at any time, t, is going to be given. It's a vector, so I'm going to use my showing. So remember, this up here is the same thing as t to the 1/2. So when you take the derivative of that, it's going to be 1/2 t to the negative 1/2, comma, the derivative of negative t is just a negative 1. So there's the velocity vector. And now I'll find the acceleration vector. So the acceleration vector, acceleration is the derivative of velocity. So a negative times that, that's going to be negative 1/4 t to the negative 3/2, comma, and the derivative of negative 1 is just 0. Okay, so there's my acceleration. And now it wants me to evaluate them each at 1. So if I wanted to evaluate the velocity at 1, I would probably take a second to rewrite this. So that's going to be equivalent, let's see, that's going to be positive 1 over 2 square root of t. Okay, so I would probably rewrite it as 1 over 2 square root of t, just because to me that makes it easier to plug into. And now it's asking what is the velocity at t equals 1, so now it's easy for me to plug in there. The square root of 1 is 1, so it's just 1/2, comma, negative 1. So 1/2, comma, negative 1, that's my velocity vector at time t, or at time 1. And now the acceleration, very similarly, I would just take a second to rewrite that. A negative exponent means I'm going to pop it into the denominator, power over root, so it'll be the square root of t cubed. And it is still negative in the numerator there, so it's going to be negative 1 over, I still have a 4, and then it'll be the square root of t cubed, comma, 0. That part's easy. And now they're asking me to evaluate that at 1. So if I plugged in a 1 there, the square root of 1 is 1. 1 cubed, still 1. That's a 4, so it just becomes negative 1/4, comma, 0. So I have that. All right. So find the velocity vector, acceleration, oh, and speed. I almost forgot the speed. So remember, speed is a scalar, right? So speed is the magnitude. Sorry, didn't realize I got cut off. So speed, remember, is the magnitude of the velocity. So speed's going to be the square root of the sum of each part of this squared. So you have to square this plus square that and then take the square root of it. So that's 1/4 plus 1, and that's going to be 5 over 4. Now remember, this square root symbol goes over the whole thing, so you could break that up into the square root of 5 over the square root of 4, which obviously is 2, so you get radical 5 over 2 is your final answer there. Next up, we got number 7. Talk about a particle's position again is given by this vector. Find its velocity vector, acceleration vector, and speed at t equals 0. So, very, very similar. We are going to find the velocity vector. So first I'm going to find the velocity with respect to time. You need to take the derivative of the position. Here's the position. The derivative of e to the t is just e to the t. And the derivative of e to the negative t is e to the negative t times the derivative of the junk, right? So that makes it a negative 1 out front. So that's like this. And then my acceleration is going to say, well, it's the derivative of this. Well, the derivative of e to the t, I could take derivatives of e to the t all day long. Still get e to the t. Now again, the derivative of this is this times the derivative of here. Well, the derivative of that's a negative 1, so it'll make it a positive again. So it'll be positive e, and it'll still be a negative t up there. So I've got my acceleration and my velocity vectors. Now it's telling me that I have to plug in t equals 0, and I have to do that before I can find the speed. So the velocity at 0, well, that's e to the 0, right, comma, minus e to the 0. Well, e to the 0 is 1, e to the 0 is 1, so that just makes this 1 comma negative 1. And my acceleration at 0, I'm just plugging 0 in there. Again, that's e to the 0, comma, e to the 0. Well, that's just 1, 1. 1, 1 for that one. Okay. And so now don't forget to find the speed. Again, speed is the magnitude of the velocity. So speed is a scalar. It's going to be a number equals the magnitude of the velocity. I'll write it like this time, just as a reminder. Oh, at 0. And that's the square root of the sum of the squares. So you take the velocity, 1 squared plus negative 1 squared, doesn't matter, right? 1 and 1. So you get square root of 2. And we've got that for number 7. All right, number 8, go ahead and try number 8 yourself. The numbers get a little bit big. I'm going to work it, and then you can check your answer. Check back in a minute. Okay, so hopefully you found the time, took those derivatives. Now be careful in there. There is a couple chain rules in there. So make sure when you're taking the derivative of this piece, for example, it's 3, this, decrease the exponent by 1, times the derivative of the inside. So you may need to take an extra line of work there to clean it up. But the idea is the same, is that from position to get to velocity, you need to take the derivative, and from velocity to get to acceleration, you need to take another derivative. So I found the velocity vector, found the acceleration vector, and I need to figure out the speed at t equals 1, so I still need to plug in 1 to each of these. So the velocity at 1, all I'm doing here is plugging in 1 into that mess. Well, 1 to the 4th, 1, so it's 5 minus 4, right? So you got 5 minus 4. And then over here, when I plug in a 1, that's 3, 4 squared is 16 times 9, right? So 9 times 16 there. And so when you clean that up, it looks like you're going to get 1 and 16, that's 144. Okay, so there's the velocity at time 1. Now I'm going to figure out the acceleration at t equals 1. Here's my acceleration right here, so I'm just plugging in 1 into there, so that's 20 minus 12. And then over here, that's going to be 4 times 54, so 54 times 4. And when you clean that up, I think you get 8 and 2, 16. So there's your acceleration. Oh, I'm running out of space. So I can squeeze my speed in over here. So remember, your speed, I'll just write it really tiny. So speed is going to be the square root of each part of the velocity squared. So 1 squared plus 144 squared. Ooh, that's going to be big. Okay. So when you do that, it'd be like the square root of 20,000, I guess. Let's see if I have, so the square root of, I don't know, 20,737, and I have to type that into my calculator. So when I type that in, I got 144.003, which makes sense, right? Because this 144 squared, and then you're just adding 1 there. So, all right, that takes care of number 8. For number 9 here, a fly is moving on the wall given by, and again we're given the position. You can tell that given the position is pretty popular, and we're given our x and our y. when is the particle at rest? So you really need to know what that means. So at rest, aka, that means that your velocity is going to be 0, 0. Now that means that both parts have to be 0. So I need to figure out the time when this piece is 0 and the time when that piece is 0, and I need to find the time that matches. That's kind of my strategy for this. So first I need to figure out the velocity. So the velocity, we're just going to take the derivative of the position, so that's 6t squared minus 24, and then a negative 4t, it'll be a plus 8. There we go. Okay, so here's my velocity, and I want it to this piece to equal that 0, this piece to equal that 0. Essentially what you're doing is you're setting each piece equal to 0. So if I set this piece equal to 0, you can factor out the 6 or move it over, either way. You're going to get 6t squared equals 24, divide both sides by 6, and you're going to get time equals plus or minus 2 there. Okay, so now I need to set this piece equal 0. So if I set this piece equal to 0, that means that negative 4t equals negative 8, and t equals positive 2. So the winner that matches is t equals 2. That's where both of them would equal 0. So for the fly to be at rest, both its horizontal position, this piece, and the vertical position, this piece over here, must be 0, and that occurs when time is 2. Okay, for number 10, part A is pretty simple. It says at which points is a tangent line curve horizontal. We've already done this. You need to know that you need to take the derivative. Well, with parametric, you've got an x of t and a y of t, so you need to do dy over dx. So you have dy dt divided by dxt. That's how you get your derivative. That's the equation for the slope. Well, we know that it has a horizontal tangent line when the numerator equals 0. When the derivative equals 0. Well, that happens when this numerator equals 0. So you set that equals 0, you solve, you get 2 times. It wanted to know what point, so you have to take those times and plug back in. So at time t equals 0, if you plug in zeros and 0 there, you get this. And if you plug in 2/3, carefully, just watch your parentheses, you get this. That's not the part I want to talk about. The interesting part is part B, at which point is the tangent line to the curve vertical. Well, we know that the tangent line will be vertical when the slope is undefined. Well, when is this slope undefined? When the denominator equals 0. So we need to set this denominator equals 0, and most people, they don't know how to do that algebraically. This one was easy to do algebraically, but we're going to put it in our y equals. So under y equals, you type it in, and you can graph that if you wanted to. Take a look at it. But really, we want to know when that equals 0. So you can see it equals 0 over here, and now we just want to figure out where that is. And you need to make sure you type it in right. I had mine typed in incorrectly, so I need to change that to this minus 5. So make sure you've got it typed in correctly before you graph it. And so now when it graphs, I could see that it definitely does cross, and to find it, you're going to do second calc, and then it's going to be choice 2, 0. So you need to go to where it crosses, a little above it, hit enter, a little below it, hit enter twice, and it's going to spit back that negative 1.13. It might be kind of hard for you to see on mine, but it does say that. So this occurs by your calculator at negative 1.1, I'm going to call it 40, okay, at that time. Once you have that, then you need to take this and plug it back into the originals. One suggestion I have for that, you might want to take this, throw it into your y1, take that, throw it into your y2, and then you could just do second calc value and then plug in negative 1.140. That might save you some time. Or, you could just carefully plug it in. Either way, so you could say at t equals negative 1.1. There, the point that you would get, I got 12.221, comma, and then negative 3.781 as my point there. Okay, so that's how you do number 10. Okay, for number 10, we're given our derivative of x here and our dy dt here, and we're given our initial position. It's asking us to find the velocity when t equals 2. Well, the velocity at 2 all we need to do, velocity means you have to plug into the derivative of position. Well, they gave me the derivative of position. So this is a tricky way of them kind of giving us that velocity. So I just need to plug in, well, cosine of 2, sine of 4, plug that into your calculator, watching your, making sure you're in radian mode, and you get there. So that one's not too bad. Write the equation of the tangent line. Same words as before. If you're writing the equation of the tangent line, you need to get to the derivative. Once you have the derivative, you plug in, and that gives you your slope. Well, the derivative. What's the derivative of this? Well, it's dy dx, and we already know that means it's dy dt over dx dt. So they gave me those. I plugged those in there, and I got t equals 1. And then when I plug in t equals 1, that's sine of 1 cos of 1. And you can type that right into your calculator. So you got sine of 1 divided by cosine of 1. And I got that 1.557 number. Okay. Next comes the acceleration. So you need to know that acceleration is the derivative of velocity. Well, we already have the velocity up in part A. So all you need to do is take the acceleration from there. So I'm going to find the acceleration at time t. Okay. So your acceleration, remember, the derivative, this really came from there. The derivative, oops, sorry, you can't see that. So the derivative of the velocity, the derivative of cos is negative sine. So it's negative sine t, comma, now the derivative of this part. Well, that's going to be a little bit of a chain rule. The derivative of sine is cos. So it's going to be cos of this thing times the derivative of the inside. So it's cosine of t squared times 2t. So you can put that 2t there if you want to. There is the acceleration formula, and now I need to plug in t equals 2 to it. And again, that's going to be straight calculator. If you're plugging in 2 in for t, you're going to end up with negative 0.909 and negative 2.615 for your acceleration. Okay. The other way you could do that is if you wanted to use this up here, if you didn't want to have to actually take that derivative because you're evaluating, you could have done it just on your calculator. Let me clear that out of there. Could have done math 8 for each part. So we're taking the derivative with respect to x of cosine of that. So close, close, and we're evaluating it at 2. So you could have gotten that 0.9 there without having to take that derivative. Now remember, that only works if you have something to evaluate. If it would have just said, you know, what's the equation for the acceleration, you would have had to actually take that derivative by hand. But because you were evaluating, you kind of got out of it. So that's kind of the good news there. Okay, so we got 2 more parts here. In part D, find the ant's position when t equals 2. So this is where, well, we know our initial position, and we know that we're going to have to use an integral. Okay, so we know the total distance, and we know where we started, right? We know the position at 1, and we're trying to figure it out, the position when t is 2. So this is what we're trying to figure out. So on your calculator, you can figure out the first part using math 9. So you've got this 0.068 equals x at time 2. That's what I'm trying to figure out. I know my x at time 1 from the very beginning of the problem was 6. So then you can just add 6 to both sides, and that tells us our position was at 6.068. So you can use that same method to find the y value. Use that same method to find the y value, and then, so if you do the same thing with the y, okay, and again, this is obtained via math 9, you get this, and that gives you your position at time equals 2, so you could put those together if you wanted to write it as a coordinate, this, comma, that. And then the last one, the total distance, that's going to be the integral. It'll be the square root of the derivatives squared. So it's this thing squared, that thing squared, and I showed you how to enter that in your calculator. And if you do that right, I got 0.739. And that is number 11. Okay, so this is on page 5. This is just graphing the polar curves. So these first 2's are going to be circles with the radius is 3 and the radius is 5. Keep in mind these circles are different than if there was, you know, the word cosine or sine after them. Remember, those would be where their left pole is at the origin or their bottom is at the origin. So just make sure you know those. But then we have roses. So the roses would be like example C, F, and G here. So kind of going there. Remember, the rose, if it's an even, like it is in this case in C and G, you need to double that number to get the number of petals, and the number out front is the length of the petals. So this is 4 petals of length 1. Over here we have 4 petals, that's even, so you double it to 4 of length 3. And then this, when it's an odd, then that is the number of petals, and that is still the length. Keep in mind that if it's a sine curve, it could either touch the y or kind of float between. And if it's a cosine, like F here and also like G, the x-axis is going to kind of cut it in half. Okay? And I can kind of sketch those in there. Okay, so notice that those cosine ones, the x-axis cuts one of the petals in half. And with the sine ones, this sine one, it's floating because it's an even and it's floating in there. And remember, these are supposed to be symmetrical, and like this is length 4, so that'd be like 1, 2, 3, 4. I just didn't draw mine perfectly. Okay? All right, then you have the limicons, and within those there's a couple different genres. You really, once you kind of get that number plus or minus a trig function, you're going to have kind of this category. Now, what you really want to do is compare the ratio of a to b. So it's this number divided by the coefficient of the trig function. So here, 1 divided by 1 is 1. That's how you get that heart shape, okay? So for this one, you're going to have a heart shape. Since it is a cosine curve and it's positive, it's going to be mostly to the right of there. So it's going to kind of have this heart shape, kind of like that. I know that's not perfectly symmetrical, right? This one should be a little smaller, but I'm just kind of sketching these. Okay, for this one over here, you've got a sine curve, or it's going to be a sine, so that tells me it's going to be either above or below. Since it's negative, this one's going to be primarily below, and it's going to have a loop. So it'll be something, oh dear, like that. Okay, with that loop, remember that ratio of a to b is a number less than 1, so less than 1 means you're going to have a loop. And down here, the number is bigger than 1, so that means you're going to have that dimple. It'll kind of look like a butt. This one's going to be primarily above, so it'll kind of be like just kind of a, it's like barely, this one kind of looks too much like, it's just barely, it's not really a heart. It's more of just like a little dimple in there. That was not really a great drawing of that one. But it's more of just a dimple there. It almost looks like a circle. And then here, again, your a divided by b is less than 1, so that's going to be loop. This one's a cosine loop, though. And so we're going to be to the right there. This one's going to be like justified to the left because of that negative. So we're going to have this loop like this. And then I'll go up like that. Okay, so that one's going to kind of have that loop in there. Probably comes a little more on this side, and I just didn't capture that great. So again, those are kind of your quick sketches of the polar graphs. Okay, remember you have to convert to rectangular, and remember you do have these equations. So we have x equals r cos theta, y equals r sine. You've got your squareds, and don't forget your tangent over there. Keeping that in mind, when you are converting, you want there to be, when you're converting to rectangular, that means you need to get rid of r's and thetas. Well, to get rid of this sine theta, I need an r with it, so I multiply both sides by r so that you get this. Now you can get rid of r squared by replacing it with x squared plus y squared, and you can get rid of r sine theta by replacing it with a y. So you've got that. All right, for number 15, we're going to go from rectangular to polar. Okay, so we know that y is r sine theta, so we can replace y with r sine theta equals 5, and a lot of times they'll get r by itself, so it'll be r equals 5 over sine theta. The only trick that they might do is they might rewrite that as 5 cosecant of theta. So we've got that. All right, find the slope, not the equation. So we're just finding the slope, okay? So basically that means we need to figure out what dy dx is, and then we need to evaluate it at pi. So we need to figure out dy dx. Well, the problem with that is I have this r. So the formula that we have to give us that says dy dx. And again, this formula is derived using the product rule here, but really it's dy d theta over dx d theta. And it's that r sine, or r cosine theta, okay, plus sine theta dr d theta over, don't forget it's going to be negative in the bottom, negative r sine theta plus cosine theta dr d theta. Alright, now from there, all you're going to do is take this r value and you're going to drop it in for the r there and there. Watch your parentheses, you're going to need a negative. And then you need to figure out what dr d theta is. So off to the side here, you can just write dr d theta equals, alright, well, the derivative of r with respect to theta, that goes away. Now the derivative of sine is cosine, so it'll be negative 2 cos theta. So negative 2 cos theta. Okay, so now all we're going to do is plug in again, we're plugging in this r, goes right here, dr d theta, so we're going to take this and plug it in right there. So let me write that down. Okay, so after you plug in for the r, you drop that r in, you drop this in for dr d theta, and then you're evaluating that at pi. So basically you're plugging in pi to there. So just for example, the sine of pi is 0, so sine of pi is 0, so this part's going to 0 out there, so you're going to have 1 minus 0 plus 0. So 1 minus 0 plus 0 is 1. In the denominator, when you plug in sine again, that this whole section here is going to end up being 0, and then here you will have 1 times negative 2 times negative will be a positive 2 there. So the slope there is going to equal 1/2. And now we're going to move on to page 6. Alright, we are almost done here. Page 6, set up but do not evaluate an integral to find the area enclosed by one loop of the graph r equals this. So this is going to be a rose with 4 petals, right? That's even, so we're going to double that number. So this is a rose with 4 petals. Now remember, you do not need to necessarily, we're just going to figure out, one of the petals. So I can sketch it real quick if you want, and it doesn't matter which petal. But this is a rose, 4 petals, and then each petal is actually going to be length 3 if you care. Okay, so we want to figure out like one petal. Basically, if I figure out where this thing equals 0, like from there to there, it'd be 0 again. So that would give me the integral that I want, because my formula for area says, right, I'm going to have 1/2, and then I'm going to have the integral, and I need these two things to be thetas, right? Because over here it's going to be a d theta. So I need to figure out those thetas first. So we're going to take this equation, and we set it equal to 0, because I'm trying to figure out my integral. So obviously divide both sides by 3, you still get a 0 over there, and then you're going to inverse, so basically cosine is going to be 0. Well, cosine, the x value, that's going to be 0. You can say negative pi over 2, or you could say pi over 2, and then at 3 pi over 2, right? And you could keep going, or you could even go negative and say negative pi over 2, negative 3 pi over 2, right? But basically then, your theta, you're going to need to divide those by 2. So you're going to get pi over 4 and 3 pi over 4 for our thetas. So I did these two, and you can tell if you, on your calculator, if you graph it, I just graphed it, and when I changed my window, I adjusted my window to be pi over 4 to 3 pi over 4, and if you graph it, you'll see that it's one petal. It's actually this petal down here, but remember, we said all the petals are the same, symmetrical and congruent, so if I find the area of one petal, then it doesn't matter which petal, basically. So our formula is going to be that 1/2, and I'm going to go from pi over 4 to 3 pi over 4, okay? And then it's going to be that thing squared. So this whole thing squared. Oop, don't forget the 3 out front, Gueli. Cos of this, and it's that whole thing squared d theta. So there's your setup. Again, if it was multiple choice, could they square each part of this, right? Could they square this and call that a 9 and then pop that out front? Absolutely they could. So just be aware that that may also be an answer choice, okay? But I'm just going to leave mine like that. All right, set up a non-evaluate integral for the inside the graph this and outside the graph of that. Okay, so this is going to be one where we're going to have to subtract. And you can set this up. I would maybe sketch this first. This looks like it's going to be a circle. This piece here is a circle. And outside the graph of our sine theta. Okay, so again, you would have to graph both of these circles without your calculator, but I just kind of wanted to show you what we're looking at. All right, so we've got a circle there and then another circle within it. So what we're looking for is, you know, this area that's, you know, kind of part of each of them, okay? And so let's see, we've got, and again, we have this circle, you know, that's going to have a diameter of 3 and it's going to be above. So 1, 2, 3. Ooh, not my best circle ever, but it'll work. And then this one is just going to have a diameter of 1, so it's really small like that. And then we're looking for the area outside, inside this and outside that. I was really confused for a second. There we go. So this is the area that we are looking for. All right, so we know that we're going to have to set up an integral, right? And we're going to have to figure out like what our bounds of integration are. To find those bounds of integration, we want to figure out where they equal each other, right? Like where they're touching. So basically what we're going to do is we're going to set these two things equal to each other. Okay, and figure out where they are equal to each other. So obviously if I move this over, that means I just have 2 of those, and it equals 0. Divide both sides by 2, still get 0. Well, theta, then sine equals 0 at 0, pi, 2 pi, right? So the first time, and if you actually watched it graph it, sometimes like that'll help you get better. So it's going to equal that, and then it'll hit it again once you get to pi. That's really what I want. So when we set up our area, I guess I'll go down here. So we know the area is going to be 1/2. We're going to integrate from 0 to pi, because that just brings me to that first time they cross. Okay, and we want to do the outside squared minus the inside squared. So this one is on the outside, and it's that whole thing squared minus. It's almost like you're doing a washer. Remember when we did the disk, it was like the disk minus the little donut that we'd have to subtract out. So minus the area of the inside thing. And again, that's going to be that whole thing squared, d theta. So there is your setup for that one. Just be aware they could, you know, square this and then bring it out, things like that. So just be aware if they factored out some coefficients from that. All right, that's it. Oh, can you see that? There we go.